There might be a planet hiding in our own solar system right now, not a tiny frozen rock like Pluto, a world roughly 4 to 10 times the mass of Earth, lurking so far from the Sun that a beam of light would need more than 2 days just to reach it. Astronomers have spent nearly a decade hunting for it. The most powerful telescopes on Earth and in orbit have scanned billions of points of light across the sky. In 2025, researchers announced the most promising candidate detection yet. And still, nobody can confirm whether Planet 9 is real. The reason is not that we lack the technology. The reason is that the outer solar system is a darkness so vast and so deep that even a giant planet can hide in plain sight. If you enjoy journeys into the most frustrating mysteries at the edge of our solar system, do me a favour and hit that like button and subscribe. It genuinely helps this channel grow and lets me keep making deep dives like this one. Let's begin. In 2003, an astronomer named Mike Brown pointed a telescope at a patch of sky near the constellation Cetus and discovered something that should not have been there. The object was small, reddish, impossibly distant, and travelling on an orbit so stretched and so extreme that it made no sense under any existing model of the solar system. Its closest approach to the Sun was 76 astronomical units. For perspective, Neptune, the most distant known planet, orbits at roughly 30 astronomical units. Pluto, the famous dwarf planet at the fringe of the Kuiper Belt, reaches a maximum distance of about 49 astronomical units. This new object never came anywhere near the gravitational influence of any known planet, not even at its closest point to the Sun. It existed in a permanent state of isolation, drifting through a region of space so cold and so dark that the Sun would appear as little more than a very bright star in its sky. At its farthest point, the object swung out to roughly 937 astronomical units, a distance so vast that sunlight reaching it would be nearly 900,000 times fainter than sunlight at Earth. A radio signal travelling at the speed of light from that distance would need more than 5 days to reach us. The full journey around the Sun would take roughly 11,400 years. When this object last occupied its current position in its orbit, human beings were still transitioning from nomadic hunting to the earliest agricultural settlements. The object was named Sedna, after the Inuit goddess of the sea who lives at the bottom of the Arctic Ocean, untouchable and alone. The name was deliberate. Sedna existed in a region of the solar system that had no business harbouring a world of that size. It was too far from Neptune to have been scattered there by gravitational kicks from the giant planets. The standard model of solar system dynamics explains most distant objects through interactions with Neptune. An icy body wanders too close to the ice giant, receives a gravitational kick, and gets flung onto a wider, more eccentric orbit. But for this mechanism to work, the object must still pass close enough to Neptune for the interaction to happen. Sedna never came within twice Neptune's distance. The scattering model simply could not explain it. At the same time, Sedna was too close to the Sun to belong to the Oort cloud, the vast theoretical shell of frozen debris that surrounds the solar system at distances of thousands to tens of thousands of astronomical units. Sedna occupied a kind of orbital no man's land, a zone between the Kuiper Belt and the inner Oort cloud that planetary scientists had assumed would be essentially empty. The discovery unsettled researchers because it demanded an explanation. Something had placed Sedna on that orbit. Something had lifted its closest approach to the Sun far above the reach of Neptune's gravity and left it stranded on an elliptical path that would take thousands of years to complete. At the time, the leading ideas ranged from a close stellar encounter in the Sun's birth cluster, which could have gravitationally nudged objects onto extreme orbits billions of years ago, to the possibility that a massive unseen body was sculpting orbits in the outer solar system right now. The second idea was provocative, but one object was not enough to build a case. One oddball orbit could always be explained away as a fluke. Then more oddballs started appearing. In 2012, astronomers Chadwick Trujillo and Scott Shepard discovered 2012 VP 113 another distant body with a perihelion of 80 astronomical units. Even farther from the Sun than Sedna at closest approach, its orbit was similarly extreme, similarly detached from Neptune's influence, and similarly difficult to explain. What caught Trujillo and Shepard's attention was not just the orbit itself, but the way it aligned with Sedna's. Both objects shared a peculiar property. Their arguments of perihelion, the angle describing where in their orbit they make their closest approach to the Sun, clustered near the same value. In a solar system governed only by the 8 known planets, there was no reason for distant objects to share this orbital alignment. Their arguments of perihelion should have been randomized over billions of years by the slow gravitational nudges of Jupiter, Saturn, Uranus, and Neptune. Instead, they lined up. Trujillo and Shepard published their findings in 2014 and noted the clustering as evidence that something massive might be lurking beyond Neptune, shepherding these orbits into alignment. The paper was cautious. 2 objects were still a thin sample, but the pattern was striking enough to catch the attention of Konstantin Batygin and Mike Brown at the California Institute of Technology, 2 researchers who would turn this tentative observation into one of the most debated hypotheses in modern planetary science. Batygin and Brown began with the data. By 2016, the catalogue of extreme trans-Neptunian objects had grown. These are bodies with semi-major axes larger than 150 astronomical units and perihelia beyond 30 astronomical units, meaning they spend their entire orbits far from the Sun and well outside Neptune's direct gravitational reach. When Batygin and Brown examined the orbits of 6 of these extreme trans-Neptunian objects, the clustering jumped off the page. Not only did their arguments of perihelion align, but their orbital planes tilted in the same direction and their long axes pointed toward the same region of the sky. The probability of this alignment occurring by chance was approximately 0.007%, less than 1 in 10,000. The 2 researchers ran dynamical simulations to test what kind of object could produce this pattern. They modeled thousands of possible configurations, varying the mass, orbit, and inclination of a hypothetical distant planet, then watching how its gravity would affect small bodies over hundreds of millions of simulated years. They found that a single massive planet on a distant, eccentric, and inclined orbit could naturally shepherd the extreme trans-Neptunian objects into the observed configuration. The planet's gravity would act as a slow gravitational fence, corralling distant objects over millions of years, pushing some into aligned orbits and scattering others onto perpendicular paths. The mechanism was not brute force. Planet 9 did not need to come close to these objects. Its influence was subtle and persistent, a gentle gravitational tide that reshaped orbits over timescales longer than the age of human civilization. Over millions of orbital periods, that gentle tide added up to a dramatic restructuring of the distant solar system. Remarkably, the simulations also predicted the existence of objects on orbits perpendicular to the main planetary plane, bodies tilted at extreme angles that seem to have no connection to the flat disk where the 8 known planets travel. Such objects had already been observed. DRAC 2008 KV42 and other high-inclination trans-Neptunian objects had puzzled researchers for years. The Planet 9 model explained them naturally. The model was not just fitting existing data, it was predicting features that had already been confirmed independently, a hallmark of a powerful scientific hypothesis. In January 2016, Batygin and Brown published their paper in the Astronomical Journal. The title was direct: Evidence for a Distant Giant Planet in the Solar System. The hypothesis they proposed became known as Planet 9. The predicted object was not a gas giant like Jupiter or a tiny frozen rock like Pluto. It sat in a mass range that the solar system had never seen before. Batygin and Brown initially estimated a mass of roughly 10 times that of Earth, placing Planet 9 in the category of a super-Earth or a mini-Neptune. Objects of this mass are the most common type of planet discovered around other stars in the galaxy. The Kepler Space Telescope revealed that planets between 1 and 10 Earth masses are extraordinarily abundant in exoplanetary systems, particularly on close-in orbits around their host stars. Yet our solar system appeared to lack one entirely. If Planet 9 existed, it would fill that gap and answer a lingering question about why our planetary family seemed to be missing its most statistically common member. The predicted orbit was extreme. Batygin and Brown estimated a semi-major axis of roughly 700 astronomical units, an eccentricity of about 0.6, and an orbital period of 10,000 to 20,000 years. At its closest approach, Planet 9 might come within roughly 280 astronomical units of the Sun. At its farthest, it could swing out to roughly 1,100 astronomical units. The orbit was also inclined roughly 30 degrees relative to the plane of the solar system, tilting it away from the flat disk where the 8 known planets travel. Over the years since that initial paper, the hypothesis has been refined repeatedly as new data arrived. Additional extreme trans-Neptunian objects were discovered by surveys around the world, and each new data point allowed researchers to tighten the constraints on Planet 9's orbit and mass. The original predictions described a broad range of possibilities, a planet that could be almost anywhere along a vast orbital arc stretching across the sky. Gradually, that range has narrowed. In 2021, Batygin and Brown updated their orbital prediction, reducing the estimated semi-major axis to roughly 460 astronomical units, and adjusting the eccentricity and inclination to better fit the expanded sample of distant objects. Then in 2025, a major study by Amir Siraj, Christopher Chiba, and Scott Tremaine at Princeton used an expanded sample of 51 extreme trans-Neptunian objects and 300 N-body simulations to further refine the parameters. Their results suggested a semi-major axis of approximately 290 astronomical units, an eccentricity of about 0.29, an inclination of roughly 6 degrees, and a mass of approximately 4.4 Earth masses. These numbers represent a significantly closer, lighter, and less inclined planet than the original 2016 prediction. The trend has been consistent. Every major update has brought Planet 9 closer to the Sun and reduced its estimated mass. If this trend continues, the planet may ultimately prove easier to detect than the earliest models suggested, but the search area remains dauntingly large. The physical properties of this hypothesized world depend heavily on its mass and formation history, but researchers have sketched plausible portraits. At 4 to 10 Earth masses, Planet 9 could be a rocky super-Earth with a thick hydrogen-helium atmosphere, or it could be an ice-rich body similar in composition to Uranus and Neptune, but smaller. Earlier models by Esther Linder and Christophe Mordesini estimated a radius of roughly 3.7 times that of Earth and a surface temperature of approximately 47 Kelvin, making it frigid but not entirely dark. Planet 9 would radiate a faint glow of internal heat, the remnant warmth left over from its formation billions of years ago, slowly leaking from its interior like embers cooling in the dead of night. That thermal emission peaks in the far infrared, at wavelengths of roughly 50 to 100 micrometers, well beyond what human eyes or optical telescopes can detect. In reflected sunlight, the object would be extraordinarily faint, perhaps magnitude 25 or dimmer, comparable to the faintest smudges that the largest ground-based telescopes can photograph with hours of exposure. At that brightness, Planet 9 would be lost among millions of background galaxies, asteroids, and cosmic ray artifacts that litter any given survey image. Finding it would be like searching for a single specific grain of dust on a beach at midnight. The 2025 refinement by Siraj and colleagues introduced another possibility that further complicated the picture. At 4.4 Earth masses, the planet's composition might lean closer to rocky rather than gaseous, more like a scaled-up Earth than a scaled-down Neptune. This distinction matters enormously for detection, because a rocky world would be physically smaller in radius than a gaseous one of the same mass. A smaller radius means a smaller cross-section for reflecting sunlight, and a smaller surface area for emitting thermal radiation. In other words, The lighter and rockier Planet 9 turns out to be, the harder it becomes to see. The very refinements that have improved our understanding of its orbit have simultaneously made it a more elusive target. But the orbital evidence is not the only reason astronomers take Planet 9 seriously. Batygin and Brown identified 4 distinct dynamical signatures that a distant massive planet would produce, and all 4 had been observed independently before the hypothesis was proposed. The first is the clustering of the longitudes of perihelion among extreme trans-Neptunian objects. The second is the confinement of their orbital planes to a similar orientation. The third is the existence of objects on highly inclined or even perpendicular orbits relative to the ecliptic, which the planet's gravity would naturally produce through a mechanism called the Kozai-Lidov effect. The fourth involves the detachment of certain trans-Neptunian objects from Neptune's gravitational influence, lifting their perihelia to distances where Neptune can no longer interact with them. Sedna was the original example, but others have followed. In 2024, Batygin and Brown published additional analysis examining low-inclination, Neptune-crossing trans-Neptunian objects. They showed that Planet 9's gravity could dynamically inject and sustain these orbits, producing observable signatures like clustered perihelia that match survey data without relying on observational biases. Each new line of evidence added weight to the hypothesis, and each made it harder to dismiss the clustering as a statistical coincidence. Yet not everyone is convinced. From the beginning, the Planet 9 hypothesis has faced serious and legitimate criticism. The most fundamental objection targets the statistical foundation of the clustering claim itself. The extreme trans-Neptunian objects used in the original analysis were discovered by different telescopes, at different times, looking at different parts of the sky. Each survey has its own selection biases. Telescopes tend to observe certain regions more than others. They are more sensitive to objects at certain distances and brightnesses. If the surveys preferentially detected objects in certain orbital configurations while missing objects in others, the apparent clustering could be an artifact of where and when astronomers looked, rather than evidence for a hidden planet. This concern is not trivial. Several independent analyses have examined the observational biases in trans-Neptunian object surveys and reached conflicting conclusions. Some studies found that the clustering remained statistically significant even after accounting for survey coverage. Others argued that the significance drops dramatically once biases are properly modelled, reducing the evidence for Planet 9 to marginal levels. The debate hinges on subtle questions about how to characterize the detection efficiency of surveys that were not specifically designed to search for extreme trans-Neptunian objects. These surveys discovered the objects incidentally while looking for other things, making their selection functions difficult to reconstruct precisely. It is a deeply frustrating situation. The strongest evidence for the most exciting possible discovery in solar system science depends on statistical arguments about telescope pointing histories and detection thresholds that few people outside the field fully appreciate. A second class of alternative explanations proposes that the clustering, if real, might arise from mechanisms other than a single massive planet. One idea involves the collective gravity of the Kuiper belt itself. If the belt of icy debris beyond Neptune is significantly more massive than currently estimated, its self-gravity could produce alignment among distant objects without requiring an additional planet. Antranik Safilian and Jihad Touma explored this possibility in 2019, showing that a sufficiently massive and extended disk of trans-Neptunian material could reproduce some of the observed clustering through secular gravitational interactions. The disk would need to contain several Earth masses of material spread across hundreds of astronomical units. The challenge with this explanation is that the required disk mass is much larger than current observations suggest, perhaps 10 times larger than the estimated mass of the known Kuiper belt, and it remains unclear whether such a massive disk could remain stable and coherent over the 4.5 billion year age of the solar system without collapsing or dispersing. Another alternative invokes the Sun's birth environment. The solar system formed within a dense cluster of young stars roughly 4.5 billion years ago, a chaotic nursery where hundreds or thousands of newborn stars jostled for space within a few light years. Close encounters with neighbouring stars during that early epoch could have perturbed the orbits of distant objects, pulling icy bodies onto extreme elliptical paths and leaving them stranded far from Neptune's reach. This mechanism works well for explaining individual objects like Sedna, but struggles to account for the precise clustering pattern that Batygin and Brown identified. Stellar flybys produce more randomized orbital perturbations rather than the tightly aligned configurations seen in the data. A more exotic suggestion appeared in 2023, when researchers showed that modified Newtonian dynamics, a theory originally proposed to explain galaxy rotation curves without dark matter, could potentially account for the observed trans-Neptunian object orbits through secular gravitational effects. This remains a minority position, and most planetary scientists consider it an unnecessarily complicated explanation for what Planet 9 can achieve with a single additional body. The honest summary, as of today, is that the Planet 9 hypothesis is the leading single explanation for a collection of gravitational anomalies in the outer solar system. It is supported by multiple independent lines of dynamical evidence. It makes testable predictions that have been partially confirmed, but it rests on a statistical foundation that remains contested, and alternative explanations have not been definitively excluded. The existence of Planet 9 is a hypothesis, not a confirmed observation. No telescope has directly detected it. No orbit has been measured. No spectrum has been taken. This distinction matters enormously. In planetary science, indirect evidence can be compelling, but it is not the same as seeing the object. The history of astronomy is littered with hypothesized planets that turned out not to exist. The most famous example is Vulcan, a planet proposed in 1859 by the mathematician Urbain Le Verrier to explain anomalies in Mercury's orbit. Le Verrier had previously used the same technique to predict the existence of Neptune. He noticed that Uranus was not following its predicted path, calculated where an unseen planet must be to explain the discrepancy, and told astronomers where to point their telescopes. Neptune was found within 1 degree of his predicted position. It was one of the great triumphs of gravitational theory. Emboldened by that success, Le Verrier applied the same logic to Mercury. The planet's orbit precessed slightly faster than Newtonian mechanics predicted. Le Verrier proposed that a small planet orbiting closer to the Sun, which he called Vulcan, was responsible. Astronomers searched for decades. Some even claim to have seen it during solar eclipses, but Vulcan did not exist. The anomalies were real, but the explanation was wrong. It took Einstein's general theory of relativity, published in 1915, to account for Mercury's orbital precession through the curvature of space-time near a massive object. No additional planet was needed. The lesson is sobering and directly relevant. Gravitational anomalies can point toward new objects, but they can also point toward new physics or incomplete understanding of existing physics. The fact that extreme trans-Neptunian objects cluster does not automatically mean a planet is responsible. It means something is happening in the outer solar system that our current models do not fully explain. Planet 9 is the most popular answer, but it is not the only one. What makes the hypothesis so tantalizing is how naturally it fits the data. The predicted planet explains not one anomaly but several simultaneously. It accounts for the clustering, the detached perihelia, the inclined orbits, and the perpendicular populations. No other single mechanism does all of this at the same time with the same elegance. Even critics of the hypothesis acknowledge that, if the clustering is real, Planet 9 is the simplest and most economical explanation. The debate is not really about whether Planet 9 could exist. The physics works. A planet of this mass on this orbit would produce exactly these effects. The debate is about whether the evidence that motivates it is robust enough to justify the extraordinary claim of a new planet hiding in our own solar system. And even among supporters, there is a wide spectrum of confidence that illustrates how genuinely uncertain this question remains. Mike Brown has publicly stated that he is extraordinarily confident Planet 9 exists, pointing to the growing number of dynamical signatures that the hypothesis correctly predicts. Other astronomers, like Sean Raymond at the Bordeaux Astrophysics Laboratory, describe their position as agnostic, saying they have gone back and forth between 90% confidence and 10% confidence, depending on which analysis they read most recently. Scott Shepard, one of the researchers who first identified the clustering, has noted that the statistics are simply not there yet to say yes or no definitively, and that discovering more extreme trans-Neptunian objects is the only way to break the deadlock. Pedro Bernardinelli, an astronomer working with the Vera Rubin Observatory data pipeline, has said he is fairly convinced Planet 9 is probably not there, but he also thinks it would be foolish not to search for it because the potential payoff of discovery is so enormous. This range of scientific opinion is itself revealing. It is rare in modern astronomy for a hypothesis to generate this level of simultaneous excitement and skepticism among experts who study the same data. Planet 9 occupies a rare and uncomfortable position in the landscape of modern science. The evidence for it is too strong to ignore and too weak to confirm. It sits in a twilight zone between discovery and speculation, supported by gravitational whispers that could be the signature of a hidden world or the echo of observational biases we do not yet fully understand. No researcher can look at the clustering data and dismiss it entirely. But no researcher can look at it and claim certainty either. The stakes are high, perhaps higher than for any observational question in solar system science since the discovery of Neptune itself. If Planet 9 is confirmed, it would be the first new planet discovered in our solar system since 1846, a span of nearly 180 years. It would fundamentally reshape our understanding of how the solar system formed and evolved. It would fill the mysterious gap in our planetary mass spectrum, the puzzling absence of a super-Earth that every other planetary system in the galaxy seems to possess. It would mean that for over a century and a half, a world larger than Earth has been orbiting our own sun and we simply never noticed. The philosophical implications alone would ripple through public consciousness. We would have to accept that even our own cosmic neighborhood, the one place in the universe we assumed we understood completely, still held a secret this large. If Planet 9 is not confirmed, if the clustering turns out to be a mirage of observational bias or the result of some other mechanism entirely, that too would be scientifically important. It would mean that the outer solar system is even stranger than a hidden planet would suggest, that processes we do not yet understand are sculpting the orbits of distant icy worlds in patterns that mimic the influence of a planet that does not exist. It would force a reckoning with our statistical methods and our assumptions about how we interpret sparse data from the edge of the known. Either way, the question demands an answer, and that answer can only come from one place, not from simulations, no matter how sophisticated, not from statistical arguments, no matter how carefully constructed, not from theoretical models, no matter how elegant their mathematics. The answer can only come from pointing a telescope at the right patch of sky, on the right night, with the right instrument, and finding the object or proving, through exhaustive and systematic search, that it is not there. This is where the story of Planet 9 shifts from theoretical physics to raw observational struggle, because finding a faint, cold, slow-moving object in the most distant and darkest reaches of the solar system turns out to be one of the hardest challenges astronomers have ever attempted. The outer solar system beyond a few hundred astronomical units is not merely far away. It is a realm where the sun's light has faded to almost nothing, where objects move so slowly against the background stars that they appear frozen in place, and where the sheer volume of space to be searched dwarfs anything astronomers have confronted before. The ghost in the orbits has left its fingerprints everywhere. But ghosts, by definition, are extraordinarily difficult to see, and this particular ghost may be hiding in the darkest room in the solar system. Here is the cruel arithmetic of the outer solar system. When you double the distance between an object and the sun, the amount of sunlight that reaches that object drops by a factor of 4. That is the inverse square law, one of the most fundamental relationships in physics. But for a distant object seen in reflected light, the punishment is even worse. Sunlight must first travel outward from the sun to the object. Then it must bounce off the surface and travel all the way back toward Earth. The reflected light that reaches your telescope has therefore made a round trip, and its brightness drops not with the square of the distance, but with the fourth power. Double the distance, and the object becomes not 4 times fainter, but 16 times fainter. Triple the distance, and it becomes 81 times fainter. Move an object from Neptune's orbit at 30 astronomical units to Planet 9's predicted distance of 300 astronomical units, and you have increased the distance by a factor of 10. The reflected light drops by a factor of 10 to the fourth power, 10,000. An object identical to Neptune in size and reflectivity, placed at 300 astronomical units, would appear 10,000 times fainter than Neptune does. Push it out to 500 astronomical units, where some orbital models have placed Planet 9 near the far end of its elliptical path, and the reflected sunlight plummets by a factor of roughly 80,000. This is not a minor observational inconvenience. This is a wall of darkness that makes even the most powerful optical telescopes on Earth strain at the very limits of their capability. To understand what this means in practice, consider how astronomers measure brightness. They use a logarithmic scale called apparent magnitude, where each step of 5 magnitudes corresponds to a factor of 100 in brightness. Neptune shines at roughly magnitude 8, faint enough to be invisible to the naked eye but easily captured by a modest amateur telescope in a few seconds of exposure. Planet 9, depending on its size, distance, and how reflective its surface is, has been predicted to appear at roughly magnitude 20 to 26. At magnitude 22, it would be about 400,000 times fainter than Neptune. At magnitude 25, it would be roughly 6 million times fainter. These are not numbers designed to inspire confidence. At magnitude 25, Planet 9 would be comparable in brightness to the faintest background galaxies visible in a deep survey image. It would be a single dim pixel among millions of other dim pixels, with nothing obvious to distinguish it from the cosmic background noise. This is the fundamental optical challenge. The outer solar system is not just far away, it is dark. The sun, which floods the inner solar system with light, becomes progressively feebler at greater distances. Stand on the surface of Planet 9 at 300 astronomical units, and the sun would still be the brightest object in the sky, but it would appear as a blazing pinpoint rather than a disk, delivering roughly 1/90,000th of the light intensity that Earth receives. The surface would be bathed in a perpetual twilight dimmer than the faintest starlit night on Earth. Any sunlight that managed to bounce off Planet 9's surface and travel back to our telescopes would carry an almost negligibly tiny amount of energy. Collecting enough of those sparse photons to form a detectable signal requires enormous mirrors, exquisitely sensitive cameras, and long exposure times. Even then, success is not guaranteed. But reflected sunlight is not the only way to find a distant planet. Every object with a temperature above absolute zero emits thermal radiation, energy generated by the internal heat of the body itself. Planet 9, even at the frigid temperatures of the outer solar system, would glow faintly in the infrared. Its predicted surface temperature of roughly 28 to 47 Kelvin means its thermal emission peaks at far infrared wavelengths between 50 and 100 micrometers. And here is the critical advantage. Thermal emission drops only with the square of the distance, not the fourth power. This means that at 500 astronomical units, Planet 9's heat signature would be roughly 278 times fainter than if the same object sat at Neptune's distance, compared to the roughly 80,000 times fainter figure for reflected light. The far infrared signal is orders of magnitude more accessible. This is why several research teams have turned to archival infrared data in their search for Planet 9. The logic is compelling. If optical telescopes are fighting against the fourth power brightness penalty, infrared telescopes face a gentler challenge. The problem is that humanity has launched very few space-based far-infrared survey telescopes, and those that did fly operated decades ago with technology that now appears primitive by modern standards. The infrared astronomical satellite, known as IRAS, launched in 1983 and conducted the first all-sky survey at infrared wavelengths. It operated for just 10 months before its liquid helium coolant ran out. Its angular resolution was modest, its sensitivity limited by the detector technology of the early 1980s, and its catalogue contained hundreds of thousands of point sources, many of which have never been fully characterized. Despite these limitations, IRAS remains one of the few instruments to have surveyed the entire sky in the far infrared. Any object emitting thermal radiation at those wavelengths, including a hypothetical distant planet, would in principle have been recorded somewhere in the IRAS data. The challenge is finding it among the noise. Japan's Akari Space Telescope, launched in 2006, conducted a more sensitive all-sky infrared survey roughly 23 years after IRAS. Akari's detectors were significantly better, and its survey reached roughly twice the depth of IRAS at comparable wavelengths. Together, the two surveys offer something invaluable for Planet 9 hunters. Two snapshots of the entire infrared sky separated by more than 2 decades. A distant planet would appear in both snapshots, but at slightly different positions, having drifted a small distance along its orbit in the intervening years. Identify a source that appears in the IRAS data and reappears in the Akari data at a position consistent with the slow orbital motion of a distant planet, and you have a candidate. This sounds straightforward in principle. In practice, it is agonizing. The far infrared sky is not a clean, dark canvas. It is a mess. The Milky Way's interstellar medium produces diffuse emission called galactic cirrus, wispy clouds of cold dust that glow at exactly the wavelengths where Planet 9's thermal signature would appear. In large swaths of the sky, particularly near the galactic plane, this cirrus emission is so bright and so structured that any faint point source buried within it becomes effectively invisible. Distinguishing a distant planet's feeble heat glow from a knot of galactic dust requires painstaking analysis and careful filtering of the data. Many candidate sources that initially look promising turn out to be nothing more than clumps of interstellar debris masquerading as point sources. Cosmic ray hits on the detectors create another source of contamination. High-energy particles striking the infrared sensors produce bright spots that mimic real astronomical sources in a single scan. Identifying and removing these artifacts requires comparing multiple passes over the same region of sky, and even then, some spurious detections slip through. The older the dataset, the harder this cleaning process becomes. IRAS data from 1983 was recorded on technology that predates the personal computer revolution. Reprocessing it with modern algorithms helps, but the original data quality imposes hard limits on what can be extracted. The Wide Field Infrared Survey Explorer, known as WISE, launched by NASA in 2009, surveyed the entire sky at shorter infrared wavelengths than IRAS or Akari, primarily between 3 and 22 micrometers. WISE was exquisitely sensitive at these wavelengths, mapping hundreds of millions of infrared sources and discovering everything from nearby brown dwarfs to distant luminous galaxies. Its extended mission, NEOWISE, continued scanning the sky for years afterward. But Planet 9's thermal emission peaks at much longer wavelengths, 50 to 100 micrometers, where WISE had no detector coverage whatsoever. WISE could in principle detect the reflected near-infrared sunlight from a distant planet, but at those shorter wavelengths the fourth power distance penalty returns in full punishing force. WISE and NEOWISE placed important constraints on the outer solar system, ruling out the existence of any Saturn-sized or larger planet within roughly 10,000 astronomical units, and any Jupiter-sized or larger object within roughly 26,000 astronomical units. These are significant results. They confirmed that no hidden gas giant lurks in the Sun's distant neighbourhood, but for a super-Earth of 5 to 10 Earth masses at 300 to 500 astronomical units, WISE simply lacked the sensitivity. The object would have been far too faint at WISE wavelengths to register as a detection. The survey effectively searched with a powerful torch, but one tuned to the wrong color of light. The story of ground-based optical surveys is similarly frustrating. Pan-STARRS, the Panoramic Survey Telescope and Rapid Response System in Hawaii, has been surveying the sky repeatedly since 2010. It photographs wide swaths of the northern sky to relatively deep magnitudes, searching for moving objects by comparing images taken on different nights. Pan-STARRS is excellent at detecting asteroids, comets, and near-Earth objects that move noticeably over hours or days, but Planet 9 moves almost imperceptibly. At 300 astronomical units, its apparent motion against the background stars would be roughly 1 to 3 arc minutes per year. That is about 1/20th of the Moon's apparent diameter per year. Over the span of a few nights, which is the typical baseline Pan-STARRS uses to identify moving objects, Planet 9 would shift by less than 1 arcsecond. That displacement is smaller than the atmospheric blurring that smears out starlight on most nights. In a single pair of images, Planet 9 would look exactly like a stationary star or a distant galaxy. Nothing about it would trigger the automated moving object detection pipelines that Pan-STARRS relies on. The Dark Energy Survey, which operated from 2013 to 2019 using the Dark Energy camera on the 4-meter Blanco telescope in Chile, faced the same fundamental problem. The survey covered 5,000 square degrees of the southern sky to impressive depth, reaching magnitude 24 or deeper in stacked images. Planet 9 could in principle have appeared in those images, but the survey's cadence was not optimized for detecting the glacial motion of a distant solar system object. The images were taken months or years apart, and the analysis pipeline was designed for cosmological measurements, not for hunting faint, barely moving dots. Dedicated reanalysis of the Dark Energy Survey data by teams searching specifically for Planet 9 ruled out portions of the predicted parameter space, but did not cover it entirely. The Zwicky Transient Facility, operating at Palomar Observatory in California since 2018, surveys the entire visible northern sky every few nights to a depth of roughly magnitude 20.5. It excels at finding transient and variable phenomena, discovering supernovae, variable stars, and fast-moving asteroids with impressive efficiency. But it simply does not go deep enough to reach Planet 9 at most of its predicted distances. At magnitude 22 or fainter, Planet 9 would be well below the Zwicky Transient Facility's single-image detection threshold. Stacking many images over time can push the effective depth deeper, but the object's slow motion complicates the stacking process considerably. To combine images effectively, you must shift each frame by the correct amount to account for the planet's movement between exposures before adding them together. Since you do not know the exact position, distance, or velocity of the object in advance, you must try thousands or millions of possible shift rates and directions, each representing a different hypothetical orbit. This technique, called shift and stack, works beautifully in principle and has been used successfully to discover faint Kuiper belt objects at 40 to 50 astronomical units. But its effectiveness degrades as the signal becomes fainter, the motion becomes slower, and the number of trial orbits grows. For Planet 9, the parameter space of possible shift rates is so large and the expected signal so feeble that shift and stack analyses require supercomputer-level processing and produce enormous numbers of false positive candidates that must each be evaluated individually. The Subaru telescope's Hyper-Suprime Cam, an extraordinarily capable wide-field camera mounted on an 8.2-meter telescope atop Mauna Kea in Hawaii, represents one of the most serious observational efforts aimed specifically at Planet 9. From 2015 to 2023, teams led by Batygin, Brown, and their collaborators used Hyper-Suprime Cam to survey predicted sky regions where Planet 9 was most likely to appear. The camera's combination of wide field of view and deep sensitivity made it well suited to the task. It could photograph a patch of sky roughly 1.5 degrees across in a single exposure, reaching magnitudes deep enough to detect Planet 9 if it happened to lie within the observed field. But the search area is vast. The orbital uncertainty for Planet 9, even with the refined 2025 parameters, spans a broad arc across the sky. Different orbital models place the planet in different constellations. Some models favor regions near Orion and Taurus. Others point towards Cetus or Eridanus. The total search area could exceed 1,000 square degrees, and hypersuprime cam photographs only about 1.5 square degrees at a time. Covering the full search area requires hundreds of separate pointings, each requiring deep exposures on multiple nights to enable motion detection. The observations consume enormous amounts of precious telescope time on one of the most oversubscribed instruments in the world. Despite years of effort and extensive coverage of high-priority areas, the Subaru Hypersuprime Cam surveys reported no confirmed detection of Planet 9. They succeeded in ruling out approximately 50% of the predicted locations for the nominal Batygin-Brown model and tightened constraints on the planet's possible semi-major axis and perihelion distance. But ruling out half the search space is not the same as finding the object. Planet 9 could simply be hiding in the other half. The Atacama Cosmology Telescope, a 6-meter millimeter wave observatory in Chile, took yet another approach. Rather than looking for reflected light or far-infrared thermal emission, it searched for Planet 9's signal at millimeter wavelengths, where the planet's cold surface would produce faint radiation detectable against the cosmic microwave background. A 2021 analysis of Atacama Cosmology Telescope data produced 10 possible Planet 9 candidates, but none could be confirmed. Millimeter wave searches have their own challenges. The angular resolution at these long wavelengths is relatively poor, making it difficult to pinpoint sources precisely, and the cosmic microwave background itself creates a noisy backdrop against which a faint point source can easily be lost. Every survey tells the same story from a different angle. Each one reached into the darkness of the outer solar system, probed a specific region of parameter space defined by wavelength, sky coverage, depth, and cadence, and came back without a confirmed detection. None of them covered the entire predicted parameter space. None of them reached deep enough at the right wavelengths to rule out all plausible versions of Planet 9. The object, if it exists, has slipped through every net that astronomers have cast so far, not because the telescopes are bad. They are extraordinary instruments, the finest ever built, but because the target is so faint, so slow, and so uncertain in position that no single survey has been able to corner it. The slowness problem deserves special emphasis because it is unlike anything astronomers typically deal with when searching for solar system objects. Near-Earth asteroids zip across the sky at rates of degrees per day. Main-belt asteroids move at arc-minutes per hour. Even Kuiper belt objects at 40 or 50 astronomical units show measurable motion over a few hours of observation, but Planet 9's enormous distance compresses its apparent motion to almost nothing. On any given night, it would appear perfectly stationary. Over a week, it would shift by less than a fraction of an arc-second, smaller than the typical measurement uncertainty for a faint source. Only by comparing observations separated by months or years can the motion become detectable, and even then, it is subtle. This glacial pace means that the standard technique for discovering solar system objects, looking for a dot that moves noticeably between two images taken hours apart, simply does not work. Planet 9 demands patience measured not in hours but in seasons. The search area problem compounds the difficulty. Even the most refined orbital models leave enormous uncertainty about where on the sky Planet 9 currently sits. The planet's orbit is elliptical, and its position along that ellipse is unknown. Different orbital phases place it in completely different parts of the sky. The orbital inclination adds another dimension of uncertainty, spreading the possible positions across a band many degrees wide. When you combine the uncertainty in semi-major axis, eccentricity, inclination, longitude of ascending node, argument of perihelion, and mean anomaly, the total sky area that must be searched runs to hundreds or potentially over 1,000 square degrees. That is a substantial fraction of the night sky. Searching it to the required depth, with the required cadence for motion detection, requires a systematic program that no existing survey was designed to carry out. The galactic cirrus problem extends far beyond a minor inconvenience. It varies on angular scales from degrees down to arcseconds, creating a lumpy, structured background that differs from one patch of sky to the next. In some directions away from the galactic plane, the cirrus is faint enough that a careful search can achieve useful sensitivity, but across enormous swaths of the sky, particularly within 20 or 30 degrees of the Milky Way's midplane, the contamination is total. A 2022 study by Sedgwick and Sargent, comparing IRAS and ACARI data, found 535 potential Planet 9 candidates after spectral energy distribution fitting, but every single one turned out to be located in a cirrus-contaminated region. Not one qualified as a credible candidate. The result was devastating. It demonstrated that galactic foreground emission acts as a natural camouflage across much of the far-infrared sky, obscuring exactly the wavelengths where Planet 9's thermal glow should be strongest. The combination of these factors creates what might be the most difficult search problem in observational solar system science. The target is faint because it is far from the Sun and small compared to the giant planets. It is slow because its enormous orbital distance translates to negligible apparent motion. It is uncertain in position because the orbit is only loosely constrained by indirect gravitational evidence. It is contaminated by foreground emission at the wavelengths where its thermal signal is strongest, and it occupies a region of parameter space where no existing survey was specifically optimized to look. Each failed survey has narrowed the possibilities. Each non-detection has sliced away a portion of the allowed parameter space, telling us where Planet 9 is not. But the remaining parameter space is still large. The planet could be closer than 300 astronomical units and fainter than expected because it is rocky and small. It could be farther than 500 astronomical units and completely beyond the reach of current instruments. It could be sitting in a region of sky contaminated by galactic cirrus, hidden in the infrared fog. It could be just barely below the detection threshold of the Subaru surveys, one magnitude too faint, lurking in the data as a noise fluctuation that nobody flagged for follow-up. This last possibility is particularly haunting. In deep survey images, the detection threshold is not a sharp line. Objects just above the threshold are confidently detected. Objects just below it are lost in noise. But objects right at the threshold inhabit a probabilistic grey zone where they might appear in one image and vanish in the next, depending on atmospheric conditions, detector noise, and background levels. Planet 9 could be existing right at this boundary in existing datasets, appearing as a marginal signal in some frames and disappearing in others, never quite bright enough to trigger a confident detection. Astronomers might have already photographed Planet 9 without recognizing it. This is not a hypothetical concern. The history of solar system discovery is full of examples where the answer existed in the data long before anyone recognized it. When Clyde Tombaugh discovered Pluto in 1930, he did so by painstakingly comparing photographic plates taken weeks apart at Lowell Observatory, searching by eye for a dot that shifted position against the fixed background of stars. Tombaugh spent months performing this excruciating comparison, blinking pairs of plates back and forth before he spotted the tiny shift that revealed the 9th planet. But Pluto had appeared on earlier photographic plates taken by other observatories. At least 2 previous images captured Pluto, including one taken at Lowell Observatory itself in 1915. Nobody had noticed. The signal was there, the detection was not. 15 years of data contained the answer, and the answer went unseen because nobody had looked at the images in precisely the right way or known exactly what to look for. The same scenario is entirely plausible for Planet 9. Somewhere in the petabytes of digital survey data accumulated over the past 2 decades by Pan-STARRS, the Dark Energy Survey, the Zwicky Transient Facility, and a dozen other programs, a faint smudge at the right position, the right brightness, and the right color might already exist, sitting in an archive on a server, waiting for the right algorithm or the right pair of human eyes to pull it from the noise and recognize it for what it is. The cumulative effect of all these searches has been to progressively tighten the constraints on where and what Planet 9 can be, without actually finding it. Scientists have ruled out large, bright versions of Planet 9 across substantial fractions of the sky. What remains is a parameter space consisting of smaller, fainter, more distant configurations that are harder to detect. The search has effectively been pruning the easy options. What remains are the hard ones. If Planet 9 exists in any of the configurations still allowed by the data, it will require deeper observations, wider coverage, more sophisticated analysis techniques, and more patience than any survey has yet provided. This is the paradox of the Planet 9 search. Every year, the hypothesis becomes better defined. The predicted mass shrinks as new simulations incorporate larger samples of extreme trans-Neptunian objects. The orbital constraints tighten as researchers refine the semi-major axis, eccentricity, and inclination. The search area narrows as certain regions of sky are systematically eliminated by non-detections. In principle, the search is converging. The allowed parameter space is shrinking. The target is being cornered. But the object itself does not get any brighter. The outer solar system does not get any closer. The fourth power distance penalty does not ease. The galactic cirrus does not clear. And the telescopes, magnificent as they are, operate within hard physical limits set by mirror diameter, detector quantum efficiency, atmospheric transparency, and the finite number of clear nights available for observation. The search is converging on an answer, but the convergence is agonizingly slow, measured in fractions of parameter space eliminated per decade, rather than detections per year. Each slice removed from the allowed region represents thousands of hours of telescope time, millions of dollars of investment, and years of careful analysis. The remaining parameter space, though smaller than it was in 2016, is still large enough to hide a planet for years to come. And yet the search has not been fruitless. It has not produced a confirmed planet, but it has produced something almost as interesting. It has produced candidates. In 2025, for the first time, multiple research teams reported infrared sources in archival data that are consistent with the predicted properties of Planet 9. These candidates emerge from exactly the kind of painstaking archival detective work that the search demands, combining decades-old data from space telescopes that ceased operating years ago. Whether any of these candidates will survive the scrutiny of follow-up observations remains an open question, but their emergence marks a turning point in the search. The hunt is no longer producing only non-detections and upper limits. It is beginning to produce leads. And those leads tell a story that is both exciting and cautionary, because a candidate for Planet 9 is a very different thing from a confirmed discovery. In April 2025, a team led by Terry Long-Fan, working with researchers from Taiwan, Japan, and Australia, published a study that sent a ripple of cautious excitement through the planetary science community. The paper described a methodical search for Planet 9 using the only two far-infrared all-sky surveys ever conducted, IRAS from 1983 and ACARI from 2006. The strategy was elegant and targeted. Planet 9, if it exists at several hundred astronomical units from the Sun, would drift slowly across the sky at roughly 3 arc minutes per year. Over the 23 years separating the two surveys, that motion would accumulate to just over 1 degree, a small but measurable shift. The team searched for sources that appeared in the IRAS catalogue at one position and in the ACARI data at a slightly offset position, with the angular separation and direction consistent with the expected orbital motion of a distant, massive body. The analysis required extraordinary care. The researchers could not simply cross-match every IRAS source with every ACARI source. That would produce millions of coincidental pairings, the vast majority of which would be unrelated objects. Instead, they worked within a specific region of the sky between 30 and 50 degrees of right ascension and -20 to +20 degrees of declination, a zone that N-body simulations by Milholland and Laughlin had identified as a promising area for Planet 9 based on dynamical models. They removed known astronomical sources by cross-matching their candidates against 9 separate optical and infrared catalogues. They filtered for sources with low background contamination to avoid the galactic cirrus problem that had crippled earlier searches, and they imposed a critical temporal criterion. Because Planet 9 would appear stationary over hours but would shift position over months, they looked specifically for Akari sources that were detected repeatedly in scans taken on the same day, but absent in scans taken months later, when the planet would have moved to a different position. This is the behavior you would expect from a slowly orbiting body, present in one location during a brief observing window, gone from that location when the telescope revisited the same patch of sky half a year later. After applying all of these filters, the team identified 13 candidate pairs, sources that appeared in both IRAS and Akari at positions consistent with slow orbital motion, at heliocentric distances between 500 and 700 astronomical units, and with estimated masses between 7 and 17 Earth masses. These numbers broadly aligned with some predictions for Planet 9, though the distances were toward the higher end of recent orbital models, and the mass range extended above the refined 2025 estimate of roughly 4.4 Earth masses. Of the 13 candidates, most were eliminated through visual inspection of the infrared images, revealing contamination from background sources, imaging artifacts, or confused emission in crowded fields. One candidate survived the full analysis. This single source appeared in the IRAS data at one position and in the Akari data at a slightly different position, with the offset matching the expected motion of a distant body over 23 years. The detection probability map built from multiple Akari scans confirmed the candidate's behavior in a particularly convincing way. It appeared on two observation dates, in June and December of 2006, consistent with a slowly moving object being caught at slightly different positions during different survey passes 6 months apart. Crucially, it was absent from other Akari scans of the same sky region taken at different times, exactly as expected for an object that had drifted out of the detector's field of view between observation epochs. The flux measurements at far infrared wavelengths, recorded at 60 and 90 micrometers, were consistent with a cold body radiating thermal energy at temperatures expected for an object at several hundred astronomical units from the Sun. The spectral shape of the emission, the ratio of brightness between the two wavelength bands, matched what models predict for a planet-sized body at those distances, rather than matching the spectral signature of a typical background galaxy or a galactic dust clump. The researchers described it as a strong candidate, noting that it satisfied multiple independent criteria predicted by Planet 9 models simultaneously: the right distance range, the right mass range, the right apparent motion, and independent detection across two separate survey epochs separated by more than 2 decades. A separate study published shortly afterward added more fuel. A team led by Chen, Goto, and Yamamura used Akari data alone, employing a different search methodology. Rather than matching sources between IRAS and Akari, they focused exclusively on the Akari single-scan detection list, searching for sources that appeared stationary over 24 hours but vanished when the same region was observed months later. Their analysis, applied to the same promising sky region, revealed 2 additional candidates whose positions and far infrared brightness fell within the theoretical prediction ranges for Planet 9. These were not the same object as Fan's candidate. They were independent detections in different parts of the search zone, each showing the hallmarks of a faint, slowly moving thermal source. The convergence of these results was striking. For years, every far infrared search for Planet 9 had come back empty or hopelessly contaminated by galactic cirrus. Now, within the span of months, 3 separate candidates had emerged from careful reanalysis of archival data. The candidates did not agree with each other in position, which meant they could not all be the same object. But collectively, they suggested that the archival infrared data might contain genuine traces of distant solar system bodies that previous analyses had missed. The researchers estimated that there was approximately a 40% chance that Planet 9 could be detectable in the unresolved infrared residuals of these surveys, a probability high enough to justify serious follow-up, but far too low to claim discovery. And that distinction matters more than anything else in this story. A candidate is not a detection is not a confirmation, and a confirmation is not a discovery until it has been independently verified by multiple observations using multiple instruments over a sufficient time baseline to determine a reliable orbit. Each of these steps represents a separate evidential threshold, and the gap between them can take years to cross. Consider what would be required to confirm any one of these infrared candidates as Planet 9. The IRAS and Akari observations are separated by 23 years, providing only 2 positional data points. 2 points define a line, and a line can suggest a direction of motion, but it cannot define a curve. A Keplerian orbit is an ellipse described by 6 parameters: semi-major axis, eccentricity, inclination, longitude of ascending node, argument of perihelion, and mean anomaly. Fitting 6 parameters from 2 data points is mathematically impossible. You need at minimum 3 widely spaced observations to begin constraining an orbit, and realistically, you need 9 or more independent astrometric measurements spread over months or years to calculate a reliable trajectory. The IRAS and Akari data give you a direction and a rough speed. They do not give you an orbit. To bridge this gap, astronomers must first recover the candidate in modern observations. The researchers proposed using the dark energy camera, a highly sensitive wide-field instrument mounted on the 4-meter Blanco telescope in Chile. The dark energy camera can reach magnitude 24 or deeper in a few hours of exposure, potentially deep enough to capture the faint reflected optical light from a distant planet. But the positional uncertainty from the 2 archival infrared detections spans a region of sky that the camera would need multiple pointings to cover. The candidate's predicted position in 2026 depends on extrapolating its motion forward from data taken in 2006, an extrapolation that assumes a straight-line trajectory over 20 years. If the actual orbit curves, as all Keplerian orbits do, the real position could differ significantly from the extrapolated one. The search area for the follow-up observation is not a single pixel on the sky. It is a region perhaps tens of arc-minutes across, requiring careful tiling of overlapping exposures and meticulous comparison with earlier images to identify anything that has moved. Even if the candidate is recovered at its predicted position, that single recovery would still not constitute confirmation. The source could be a background object, a distant galaxy, or a galactic source that happened to lie at the right position in both IRAS and Akari by coincidence. Confirming that the source is a solar system body requires detecting its motion against the fixed background stars over subsequent observations separated by weeks or months. Only when multiple observations reveal a consistent pattern of slow, steady motion, compatible with a heliocentric orbit at the predicted distance, can astronomers begin to calculate orbital elements. And only when those orbital elements are sufficiently well determined to predict the object's future position, and the object is found at that predicted position, does the detection become a credible discovery. This multi-step confirmation process can take a long time. The history of outer solar system discovery provides instructive examples. When Sedna was discovered in 2003, its orbit was so elongated and its motion so slow that years of follow-up observations were required to pin down its orbital parameters with confidence. Even the much closer and brighter dwarf planet Eris, discovered in 2005 at roughly 97 astronomical units, required months of astrometric follow-up before its orbit was reliably determined. For an object at 500 or more astronomical units, moving at perhaps 1 to 2 arc-minutes per year, the timeline for orbital determination stretches even longer. Months of observations might yield only a few arc-seconds of total displacement, barely enough to distinguish from measurement noise. Meanwhile, at the other end of the solar system, an entirely different kind of discovery was complicating the Planet 9 narrative. In July 2025, a team using the Subaru telescope's Hypersuprime cam announced the discovery of a new member of one of the rarest classes of objects in the solar system. The object, officially designated 2023 KQ-14 and nicknamed Ammonite, by the discovering team after the ancient fossilized cephalopod was a sednoid, the fourth ever found. The name was chosen because the fossil survey that discovered it uses the analogy of paleontology, treating these distant icy bodies as frozen relics preserving information about the solar system's earliest history. Sednoids are trans-Neptunian objects with perihelion distances greater than roughly 60 astronomical units and semi-major axes greater than 200 astronomical units, placing them far beyond Neptune's gravitational influence in the same orbital no-man's land that Sedna inhabits. These are objects that have been gravitationally detached from the known planets for billions of years. Whatever placed them on their current orbits did so early in the solar system's history, and those orbits have remained essentially unchanged ever since, like fossils preserved in stone. Ammonite was first detected in observations from March, May and August of 2023. Follow-up observations with the Canada-France-Hawaii telescope in July 2024 refined its orbit, and recovery images were identified in archival data from the Dark Energy camera dating back to 2014 and 2021, as well as images from Kitt Peak National Observatory from 2005. This 19-year baseline of observations allowed the team to determine Ammonite's orbit with high precision. The object has a semi-major axis of roughly 252 astronomical units, an eccentricity of about 0.74, and a perihelion distance of 66 astronomical units, making it the third most distant perihelion among known trans-Neptunian objects. Its estimated diameter lies between 220 and 380 kilometers, making it a possible dwarf planet candidate. At the time of discovery, it was approximately 71 astronomical units from the Sun, near the closest point in its orbit, which is the only reason it was detectable at all. At its most distant point, Ammonite recedes to over 400 astronomical units, far beyond the reach of any current survey. The previous three known sednoids, Sedna, 2012 VP113, and Liliakuhunua, had been key pieces of evidence motivating the Planet 9 hypothesis. Because their orbits appeared to cluster in a similar direction, Ammonite changed the picture. Its orbit did not align with the other three sednoids. While the first three known sednoids had their longitudes of perihelion clustered between 0 and 90 degrees, Ammonite's longitude of perihelion sat at approximately 271 degrees, pointing in nearly the opposite direction. This anti-alignment was not what the simplest versions of the Planet 9 hypothesis predicted. If a massive planet were shepherding sednoid orbits into a persistent cluster, all sednoids should eventually be corralled into similar orientations. Ammonite was moving to the beat of a different gravitational drum. The discovery team, led by Yingtung Chen and collaborators working with the formation of the outer solar system, an icy legacy survey, ran numerical simulations to understand what Ammonite's orbit implied. They found that Ammonite's orbit was dynamically stable over 4.5 billion years, meaning it had likely remained on this path since the earliest days of the solar system. More intriguingly, their simulations suggested that all four sednoids may have shared a common orbital alignment roughly 4.2 billion years ago, about 300 million years after the solar system formed. Over the intervening eons, the slow differential precession of their orbits, caused by the gravitational influence of the known giant planets, had gradually spread their orbital orientations apart. Ammonite had simply precessed farther from the original cluster than the others. This result offered two very different interpretations depending on your prior beliefs about Planet 9. If you supported the Planet 9 hypothesis, you could argue that the original clustering 4.2 billion years ago was caused by a massive planet that may or may not still be present. Perhaps the planet existed early in solar system history, sculpted the sednoid orbits into alignment, and was later ejected through a gravitational interaction with the other giant planets. This would explain the primordial clustering without requiring a planet that is still there today. Alternatively, if Planet 9 is still present, its orbit would need to lie farther from the Sun than some earlier models predicted, at distances large enough that its gravitational influence would not destabilize Ammonite's current orbit over 1 billion years. The 2024 orbital prediction of a semi-major axis around 500 astronomical units could accommodate this, but just barely. If you were skeptical of Planet 9, Ammonite handed you a powerful new argument. The fact that the fourth sednoid discovered broke the orbital alignment that had originally motivated the hypothesis weakened the statistical case for clustering. With only 3 aligned objects and 1 misaligned object, the apparent pattern looked less convincing. Yukun Huang of the National Astronomical Observatory of Japan, who conducted the orbital simulations for the Ammonite study, stated directly that the misalignment lowered the likelihood of the Planet 9 hypothesis. He suggested that a planet may have once existed in the outer solar system but was subsequently ejected, a scenario known as the rogue planet encounter model. In this picture, a massive body passed through the outer solar system during its turbulent youth, perturbed the orbits of primordial icy bodies, and then departed, either flung out of the solar system entirely or captured onto an orbit too distant and too faint to detect. The rogue planet encounter model is not new. It has been proposed independently by several research groups as an alternative to the persistent Planet 9 scenario. The key difference is that a rogue encounter is a one-time event. It shapes orbits and then the perturber disappears. Planet 9, by contrast, is supposed to be there right now, continuously influencing the outer solar system. Ammonite's orbit is more naturally explained by a one-time perturbation followed by billions of years of unperturbed precession than by ongoing gravitational shepherding from a present-day planet. But neither explanation can be definitively confirmed or excluded with only 4 sednoids known. The sample is simply too small. This is one of the deepest frustrations of the Planet 9 debate. Every new extreme trans-Neptunian object discovered adds information, but the objects are so rare and so hard to find that the sample grows achingly slowly. Sedna was found in 2003. 2012, VP113 appeared 9 years later. Leliakuhonua was discovered in 2015. Ammonite arrived a full 8 years after that, 4 objects in 22 years. The statistical power of a 4-object sample to discriminate between competing hypotheses is vanishingly small. Researchers can run sophisticated simulations and Bayesian analyses, but when your entire dataset fits on one hand, the conclusions will always carry enormous uncertainty. The Vera Rubin Observatory is expected to change this dramatically by discovering tens of thousands of new trans-Neptunian objects, potentially including dozens of extreme objects in the sednoid class. But those discoveries will accumulate over years of survey operations, and the orbital characterization of each new object requires extended follow-up observations. The sample size problem will ease, but it will not disappear overnight. While some researchers hunted for Planet 9 in infrared archives, and others debated the meaning of sednoid orbits, a small but persistent thread of the story explored an even more radical possibility. What if the gravitational anomalies in the outer solar system are not caused by a planet at all? What if the object responsible is something far stranger? In 2019, physicists Jakob Schultz at Durham University and James Unwin at the University of Illinois at Chicago published a paper that reframed the Planet 9 question entirely. They noted that the gravitational evidence for Planet 9 depended only on mass, not on what kind of object that mass belonged to. A planet of 5 to 10 Earth masses would produce the same orbital perturbations as any other object of the same mass at the same distance. The gravitational fingerprints would be identical. Schultz and Unwin proposed that instead of a planet, the object might be a primordial black hole, one of a hypothetical population of small black holes that may have formed in the extreme density fluctuations of the very early universe, fractions of a second after the Big Bang. A primordial black hole of 5 to 10 Earth masses would be astonishingly small by human standards. Its event horizon, the boundary from which not even light can escape, would measure roughly the diameter of a tennis ball. Despite containing several times the mass of our entire planet, the object would fit comfortably in the palm of your hand if you could somehow hold it without being destroyed by its gravity. It would be invisible at every wavelength of light. No infrared telescope, no optical survey, no radio dish could detect it directly because it would emit no electromagnetic radiation of any kind, apart from a negligible trickle of Hawking radiation far too faint to ever measure from Earth. It would be the ultimate dark object, exerting gravitational influence on everything around it while revealing nothing about itself through any form of light. The only way to detect a primordial black hole in the outer solar system would be through its gravitational effects on nearby matter or through indirect signatures. If it possessed a halo of accreted dark matter, as some theoretical models predicted, that halo might produce a faint signal in X-rays or gamma rays through dark matter particle annihilation. Siraj and Loeb later proposed that the Vera Rubin Observatory might detect brief flares of visible light produced when the black hole encountered and consumed small icy bodies or cometary debris in the outer solar system. But detecting such transient signals from hundreds of astronomical units away would require extraordinary sensitivity, precise knowledge of where to point the instruments, and a great deal of luck. The primordial black hole hypothesis attracted significant media attention because of its dramatic implications, but within the scientific community, it remained a decidedly minority position. Konstantin Batygin, one of the original architects of the Planet 9 hypothesis, commented that while the primordial black hole scenario was technically possible, there was currently not enough evidence to make it more plausible than the far simpler explanation of a planet. The hypothesis solved no additional problem that the planet model did not already address, and it introduced new assumptions about the existence and abundance of primordial black holes that were themselves unverified. It was, as one physicist put it, an interesting thought experiment rather than a leading explanation. Nevertheless, the primordial black hole idea illustrated an important point about the nature of the Planet 9 problem. The gravitational evidence tells us that something with a certain mass is influencing the outer solar system. It does not tell us what that something is. A super-Earth, a mini-Neptune, a captured rogue planet, a primordial black hole, even a dense cluster of smaller objects that collectively mimic the gravitational signature of a single large body, all of these are formally consistent with the indirect evidence. Only direct detection can resolve the ambiguity, and direct detection is exactly what has proven so maddeningly difficult. The 2025 infrared candidates from the IRAS and Akari analyses are relevant here because they offer a potential way to discriminate between some of these possibilities. If follow-up observations confirm that one of the candidates is a real, moving, thermal source at hundreds of astronomical units, it would immediately rule out the primordial black hole hypothesis. Black holes do not emit far-infrared radiation. A confirmed thermal detection would mean the object is a physical body with a surface temperature, reflecting or emitting electromagnetic radiation in ways consistent with a planet or a large icy body. This is one reason the infrared candidates, even in their unconfirmed state, carry such scientific weight. They are not just potential detections of Planet 9, they are potential eliminators of alternative hypotheses. But the candidates also highlight the profound difficulty of the confirmation process. A source appearing in two archival datasets separated by 23 years, each with limited angular resolution and significant noise contamination, is far from a slam dunk detection. The possibility of coincidental alignment with a background source, a galactic cirrus knot, or an imaging artifact is real and must be rigorously excluded before any stronger claim can be made. The researchers who published these results were careful to describe them as candidates requiring follow-up, not as probable detections. The language of science is precise for good reason. Every premature announcement of a major discovery that later falls apart erodes public trust and scientific credibility. The current state of the Planet 9 search can be summarized with uncomfortable honesty. The indirect gravitational evidence remains intriguing, though it has been partially complicated by the discovery of ammonite. The infrared candidate detections from 2025 are the most promising direct leads ever produced, but they remain unconfirmed. The primordial black hole hypothesis offers a creative alternative but lacks independent support. No confirmed detection exists. No trajectory has been calculated from direct observation. No physical properties have been measured from the object itself. What has changed is the trajectory of the search. For nearly a decade after Batygin and Brown's 2016 paper, the Planet 9 hunt was defined almost entirely by non-detections. Survey after survey came back empty. Each null result eliminated a portion of parameter space but brought no closer to resolution. The emergence of infrared candidates in 2025 shifted the narrative for the first time. The search now has specific targets that can be tested with existing instruments on realistic timescales. If follow-up observations with the dark energy camera or other deep imaging facilities recover one of these candidates as a moving source, the confirmation process can begin in earnest. If they do not, the candidates will join the long list of false alarms and the search will continue. Either way, the fundamental challenge remains. The outer solar system is vast, dark, and poorly mapped at the wavelengths and depths required to detect a body like Planet 9. Even if a candidate is recovered, the glacial pace of confirmation means that years of additional observations will be needed to determine an orbit. And even if an orbit is determined, the extraordinary nature of the claim, a new planet in our own solar system, demands extraordinary evidence. The scientific community will rightly insist on independent verification from multiple observatories before accepting such a discovery as real. The distance between a candidate and a confirmed planet is not measured in astronomical units. It is measured in years of patient, painstaking, unglamorous observational work. And the most powerful instrument ever designed for this specific task is only now beginning to open its eyes. On the evening of June 23, 2025, a new telescope opened its mechanical eyes for the first time from a mountaintop in Chile's Atacama Desert, the Vera C. Rubin Observatory, perched 8,700 feet above sea level on the summit of Cerro Pachón, captured its first images of the southern sky and released them to the world. The moment had been more than 2 decades in the making. Planning for the observatory began in the late 1990s. Construction started in 2015. Delays caused by a global pandemic pushed the timeline back by years. But when the observatory finally achieved first light, the astronomical community understood that a new era of sky survey science had begun. The instrument at the heart of the observatory is the largest digital camera ever constructed for astronomical research. The camera weighs roughly 6,200 pounds and contains 3,200 megapixels spread across 189 individual sensors. It is roughly the size of a small car. When mounted inside the Simonyi Survey telescope, an 8.4-meter optical system designed specifically for wide-field imaging, this camera can photograph a patch of sky 3.5 degrees across in a single 5-second exposure, reaching depths that would have required hours of integration with previous generation instruments. The combination of enormous field of view, extraordinary depth, and rapid slewing means that the Rubin Observatory can photograph the entire visible southern sky every few nights, building up a continuous motion picture of the cosmos that no previous telescope could match. The observatory's primary mission is the Legacy Survey of Space and Time, a 10-year program designed to image the southern hemisphere sky repeatedly, night after night, for a full decade. Full survey operations are planned to begin in early 2026, following a commissioning phase that produced the first test images in late 2025. Over those 10 years, the survey will generate approximately 20 terabytes of raw data every night, accumulating a total archive that will dwarf every previous astronomical survey combined. The system will issue up to 10 million alerts within 60 seconds of detecting any change in the sky. A new supernova, a moving asteroid, a variable star, or a faint dot that was not there before. The automated alert system will compare every new image against a deep reference template built from earlier observations, flagging anything that has moved, brightened, faded, or appeared for the first time. The first alerts were generated in February 2026, marking the beginning of what astronomers describe as the most ambitious time domain survey in the history of ground-based astronomy. This relentless nightly comparison is precisely the capability that the Planet 9 search has lacked for decades. Previous surveys took snapshots. Rubin takes a movie. Every previous survey that searched for Planet 9 was limited by one or more critical constraints. Some lacked the depth to see faint objects at hundreds of astronomical units. Others lacked the sky coverage to search the full predicted orbit. Still others lacked the cadence to detect the glacial, apparent motion of a distant body. The Rubin Observatory is the first instrument designed from the ground up to address all three simultaneously. Its mirror collects enough light to reach magnitude 24.5 in a single image, and magnitude 27.8 when all 10 years of data are stacked together. Its field of view covers enough sky to survey the entire southern hemisphere systematically, and its nightly cadence means that slow-moving objects will accumulate a trail of detections over weeks, months, and years, allowing even the most sluggish outer solar system bodies to be identified through their creeping drift against the background stars. Astronomers have estimated that if Planet 9 exists within the brightness and distance ranges currently predicted, the Rubin Observatory has a 70 to 80% chance of detecting it. Scott Shepard of Carnegie Science, one of the researchers who first identified the orbital clustering that motivated the hypothesis, has described Rubin as the best bet to find Planet 9 in the next few years. Megan Schwamb, a planetary astronomer at Queen's University Belfast working with the Rubin data pipeline, has suggested that Planet 9 could be found within the first year or two of full survey operations if it lies in the more accessible parts of its predicted orbit. Mike Brown, the Caltech astronomer who co-authored the original Planet 9 hypothesis, has said that if he could design a telescope specifically to hunt for this planet, he would build something very close to the Vera Rubin Observatory. But a 70 to 80% chance of detection is not a certainty. It leaves a 20 to 30% probability that Rubin will search for a decade and find nothing. This residual uncertainty is not a flaw in the observatory. It is a reflection of how poorly constrained the target remains. If Planet 9 is on the smaller end of its predicted mass range, perhaps 3 or 4 Earth masses rather than 10, it would be physically smaller and reflect less sunlight. If its surface is dark, covered in carbon-rich ices or tholins that absorb rather than reflect incoming photons, its apparent magnitude could drop below Rubin's single image detection threshold. If it currently sits near the far end of its eccentric orbit, hundreds of astronomical units farther from the Sun than the most optimistic predictions, it would be fainter still. And if it happens to lie in a region of sky crowded with background galaxies or contaminated by scattered light from bright foreground stars, automated detection algorithms might struggle to pick it out from the noise, even if it technically falls within Rubin's sensitivity range. Samantha Lawler, an astronomer at Campion College in Canada, has made this point explicitly. Even if the Rubin Observatory does not find Planet 9 during its initial years of operation, that does not necessarily mean the planet is not there. It could be farther out, smaller, or less reflective than current models assume. Absence of evidence, in this case, would not be evidence of absence. It would simply mean that the allowed parameter space for Planet 9 has been pushed into configurations that are even harder to detect. There is also the question of what happens after detection. Suppose the Rubin Observatory identifies a faint, slowly moving source at a distance of 300 astronomical units, consistent with the predicted properties of Planet 9. The discovery would make headlines around the world, but the scientific process would only be beginning. A single detection provides a position and a brightness. It does not provide an orbit. To determine the orbit, astronomers must track the object across multiple observations spanning months or years, measuring its position with sufficient precision to fit the 6 orbital parameters that describe its path around the Sun. At 300 astronomical units, Planet 9's apparent drift would amount to only a few arc minutes over an entire year of Rubin observations, a displacement enough to confirm that the object is moving, but potentially insufficient to distinguish between a circular orbit at moderate distance and a highly elliptical orbit at much greater distance. The orbital determination problem is more subtle than it appears. For objects in the inner solar system, even a few weeks of observations spanning a significant arc of the orbit can yield a reliable trajectory. Asteroid hunters routinely calculate orbits from 3 or 4 observations separated by days, but Planet 9's orbital period is measured in thousands or tens of thousands of years. A decade of Rubin observations would capture less than 0.1% of the full orbit. The object would appear to move in an almost perfectly straight line across the sky, with only the faintest hint of curvature betraying the elliptical nature of its path. Extracting that curvature from the noise of astrometric measurement errors requires extraordinarily precise positional data accumulated over the longest possible baseline. Atmospheric turbulence, detector systematics, and the finite precision of star catalogues used for positional reference all introduce errors that must be beaten down through repeated measurement. Realistically, pinning down Planet 9's orbit to the level of confidence required for a formal discovery announcement could take 5 to 10 years of sustained follow-up observations after the initial detection. That is 5 to 10 years of dedicated telescope time, careful astrometry, and painstaking orbital fitting before the word planet can be attached to the object with scientific confidence. During that time, the candidate would exist in a state of scientific limbo, too promising to ignore, too uncertain to celebrate. The astronomical community would know that a strong candidate had been identified. Papers would be published analysing every available photon of data. Theorists would run simulations attempting to constrain the orbit from the limited astrometric arc. Debates would intensify between those convinced the candidate was genuine and those who counselled patience. Media coverage would oscillate between breathless excitement and cautious skepticism. The public would want a definitive answer. Science would not yet have one. But the formal recognition of a new planet, the kind of announcement that changes textbooks, rewrites the census of our solar system, and earns a permanent name from the International Astronomical Union, would remain on hold until the orbit was sufficiently well determined to predict the object's future position with confidence. Only when other observatories independently recover the object at its predicted location, confirming that it follows the calculated orbital path, would the discovery be considered secure. This is the standard that planetary science demands. Anything less would risk a repetition of the embarrassments that have occasionally marred the history of claimed planetary discoveries. This extended timeline highlights a reality about outer solar system science that is difficult for the public to appreciate. Discovery in the outer solar system is not a single dramatic moment. It is a slow, iterative process that unfolds over years. Sedna was discovered in 2003, but its orbital parameters continued to be refined for years afterward, as additional observations accumulated. Eris, discovered in 2005 at roughly 97 astronomical units, required sustained follow-up before its orbit and mass were precisely determined. For Planet 9, potentially 5 to 10 times more distant than Eris, the confirmation timeline would be correspondingly longer. The announcement of a candidate might come in 2027 or 2028. The confirmation of a planet might not arrive until the mid-2030s. And even the Rubin Observatory cannot search the entire sky. Its location in the southern hemisphere means it can observe only the sky visible from Chile, roughly the southern 70% of the celestial sphere. Planet 9's predicted orbit, depending on which model you use, places it in different parts of the sky. Some models favour the southern sky, which Rubin covers well. The 2025 refinement by Siraj and colleagues suggested that Planet 9's current position might place it within the field of view of Rubin's early observations, which would be ideal, but other models point toward regions of the northern sky that Rubin cannot reach. If Planet 9 happens to lie north of Rubin's accessible zone, the Subaru telescope in Hawaii, with its Hyper-Suprime Cam, remains the primary Northern Hemisphere search instrument. Subaru has already spent years searching without success. Its future campaigns will benefit from the tighter orbital constraints provided by new simulations, but it covers far less sky per night than Rubin, and must compete for observing time with dozens of other scientific programs. Beyond the direct imaging search, the Rubin Observatory will contribute to the Planet 9 question through a less dramatic but equally important channel. Over its 10-year survey, Rubin is expected to discover approximately 37,000 new trans-Neptunian objects, expanding the current catalogue by a factor of 10 or more. This is not a marginal improvement, it is a revolution in outer solar system demographics. Among these tens of thousands of new objects will be dozens of new extreme trans-Neptunian objects, bodies with semi-major axes greater than 150 astronomical units, whose orbits are sensitive to the gravitational influence of a distant planet. Each new extreme trans-Neptunian object provides another data point for testing whether the orbital clustering that motivated the Planet 9 hypothesis is real or an artifact of observational bias. The current sample, fewer than 24 objects in the loosest definition, is simply too small to deliver a definitive statistical verdict. Rubin will change that. This statistical approach matters because it addresses the deepest weakness of the current evidence. As of today, the entire Planet 9 hypothesis rests on the orbital properties of a small number of extreme trans-Neptunian objects, fewer than 24 in the most generous counting, and only a handful in the strictest definition. The discovery of Ammonite, with its anti-aligned orbit, demonstrated how a single new object can shift the statistical picture. A sample of 50 or 100 extreme trans-Neptunian objects would either confirm the clustering pattern beyond reasonable doubt or dissolve it entirely. If the clustering strengthens as the sample grows, Planet 9 becomes harder to dismiss, even if no direct detection is made. If the clustering fades, the hypothesis weakens regardless of how much sky Rubin surveys. This indirect statistical test may ultimately prove more decisive than any single detection. The Planet 9 hypothesis lives or dies on the clustering evidence. If Rubin's flood of new trans-Neptunian object discoveries reveals that the apparent alignment was a small number statistical fluke amplified by observational bias, the motivation for the search evaporates. There might still be undiscovered planets in the outer solar system, but they would not be required to explain the orbital data. The search would continue out of scientific curiosity rather than theoretical necessity. Conversely, if the clustering survives the expansion of the trans-Neptunian object catalogue, it becomes one of the most compelling pieces of circumstantial evidence in planetary science. A confirmed, statistically robust clustering pattern among distant orbits would essentially demand an explanation, and Planet 9 would remain the most economical one. At that point, the pressure to find the object directly would intensify enormously. Every telescope capable of reaching the required depth would be enlisted. Archival data from every survey would be reanalyzed with updated orbital predictions. The hunt would become one of the highest priority programs in ground-based astronomy. But there is a scenario that nobody in the field talks about publicly yet deserves serious consideration. What if the clustering is real? The gravitational evidence is robust, and yet no planet is found. What if Rubin surveys the southern sky for a decade? Subaru covers the north, archival infrared data is mined to exhaustion, and the combined search rules out every plausible combination of mass, distance, and albedo for a planetary body? This would not be a failure. It would be a profound scientific result, arguably as important as finding the planet itself. It would mean that something is producing the observed gravitational anomalies in the outer solar system, but that something is not a conventional planet detectable through reflected light or thermal emission. It could be a primordial black hole, invisible to all electromagnetic searches, identifiable only through its gravitational influence or the occasional flare produced when it consumes a passing icy body. It could be a distributed population of smaller bodies, perhaps hundreds of Pluto-mass objects scattered through the outer solar system, whose collective gravitational influence mimics the effect of a single massive perturber. It could be evidence for modified gravitational physics operating at the outermost edges of the solar system, where accelerations are extremely small and general relativity might behave differently than in the stronger gravitational fields closer to the Sun. Or it could be something nobody has yet imagined, a phenomenon that lies outside the current theoretical framework entirely. The history of astronomy teaches that the universe routinely delivers answers that were not among the original options presented to the scientists asking the questions. When astronomers searched for Vulcan, a planet supposed to explain Mercury's orbital anomalies, they found general relativity instead, a fundamentally new understanding of gravity itself. When engineers at Bell Labs searched for the source of persistent radio static contaminating their communications antenna in 1964, they stumbled upon the cosmic microwave background, the afterglow of the Big Bang. When astronomers searched for dark stars or massive compact objects that might explain why galaxy rotation curves defied Newtonian predictions, they found dark matter, a substance that constitutes 85% of all matter in the universe, and yet remains unidentified after half a century of effort. The outer solar system may be preparing a similar surprise. The gravitational anomalies that motivated the Planet 9 hypothesis are real. Something is happening out there. But the assumption that it must be a planet, while reasonable and currently the leading explanation, is not guaranteed to be correct. Nature is not obligated to match our hypotheses. This is where the story of Planet 9 transcends a simple search for a missing object and becomes something deeper. It becomes a story about the limits of human knowledge at the edge of our own cosmic neighborhood. We have mapped the surfaces of Mars and the moons of Jupiter. We have sent spacecraft to Pluto and the Kuiper Belt. We have catalogued billions of stars in our galaxy and measured the expansion rate of the universe itself. And yet, within our own solar system, a region of space that we have been observing for centuries, there may be a world several times the mass of Earth that we cannot find. The outer solar system, beyond a few hundred astronomical units, is one of the least explored territories in all of science. We know more about the surfaces of galaxies billions of light years away than we know about the population of objects orbiting our own sun at distances greater than 200 astronomical units. The reason is simple and sobering. Those distant galaxies are bright. They emit copious amounts of light across many wavelengths. The outer solar system is dark. Its inhabitants reflect almost nothing and emit only the faintest whisper of thermal radiation. Brightness, not distance, is the currency of astronomical discovery. A galaxy 10 billion light-years away can outshine a planet 300 astronomical units from the Sun. The universe has arranged things so that the edge of our own neighborhood is among the hardest places to see. This observational blindness has consequences that extend beyond the Planet 9 debate. If a planet of 4 to 10 Earth masses can remain undetected at a few hundred astronomical units, what else might be hiding out there? Computer simulations of solar system formation suggest that the outer regions may contain far more material than we currently account for. Rogue planets captured from the Sun's birth cluster, icy bodies ejected during the turbulent early era of giant planet migration, and debris from long-forgotten collisions could populate the space between the Kuiper Belt and the inner Oort cloud in numbers we have not begun to estimate. Ammonite, with its fossilized orbit, is almost certainly not the last surprise waiting in that darkness. It is a single specimen in what may be a vast, unseen graveyard of primordial objects. The Vera Rubin Observatory will open a window into this hidden realm. It will not illuminate all of it, no single telescope can, but it will reveal more of the outer solar system than all previous surveys combined. Over 10 years, it will build the deepest, widest, most temporally complete map of the moving sky ever created. Objects that have drifted unnoticed through existing surveys for decades will be caught by Rubin's relentless nightly imaging. Some of those objects will be mundane, others will be extraordinary, and one of them, perhaps, will be the planet that has eluded every search for the past decade. Or perhaps not. Perhaps Planet 9 will remain hidden even after Rubin completes its survey. Perhaps the darkness beyond Neptune will keep this particular secret for another generation of astronomers, who will build even larger telescopes, launch new infrared observatories into space, and develop analysis techniques that we cannot yet imagine. The outer solar system has no obligation to reveal itself on our schedule. It exists on timescales measured in billions of years and at distances measured in hundreds of astronomical units. Human impatience, however understandable, does not change the physics. The honest conclusion is not a dramatic reveal or a confident prediction. It is something quieter and more unsettling. Planet 9 may be real. The gravitational evidence is suggestive, though not conclusive. The infrared candidates are intriguing, though not confirmed. The orbital predictions have been refined over a decade, though they still span a wide range of possibilities. The most powerful survey telescope ever built is about to begin searching with capabilities that dwarf every previous effort. If Planet 9 exists within the predicted parameter space, there is a strong chance it will be found within the next decade. But that chance is not a certainty, and the outer solar system is large enough, dark enough, and poorly enough understood that a negative result would not close the book. It would simply turn the page to a chapter we have not yet written. The phrase "impossible to find" does not mean the search is hopeless. It means the search is operating at the ragged edge of what observational science can achieve. The target is extraordinarily faint. The search area is extraordinarily large. The motion is extraordinarily slow. The confirmation process is extraordinarily long. And the fundamental uncertainty about whether the object exists at all adds a layer of existential difficulty that most astronomical searches do not face. Astronomers hunting for exoplanets know that planets exist around other stars. Astronomers hunting for gravitational waves knew that merging black holes exist somewhere in the universe. Astronomers hunting for Planet 9 do not have that luxury. They are searching for an object whose existence is inferred but not proven, whose properties are estimated but not measured, and whose location is predicted but not known. Every night of telescope time devoted to the search is a gamble, a well-reasoned, scientifically justified gamble, but a gamble nonetheless. This is what makes the Planet 9 story so compelling and so human. It is a story about reaching into the darkness and not knowing what you will find. It is a story about the gap between what we can infer and what we can see. It is a story about the outer edge of our solar system, a place that should be familiar because it orbits our own star, and yet remains as mysterious as the most distant reaches of the observable universe. The sun has been burning for 4.5 billion years. Its light has been illuminating the planets, the moons, the asteroids, and the comets of this system for longer than complex life has existed on Earth. And still, beyond a certain distance, that light becomes too feeble to reveal what is there. We do not know if Planet 9 exists. We do not know if the infrared candidates are real. We do not know if the orbital clustering will survive the expansion of the Trans-Neptunian Object Catalogue. We do not know if the Vera Rubin Observatory will find a new planet or a deeper mystery. What we do know is that the outer solar system is not the empty void that textbook diagrams suggest. It is a frontier, dense with unanswered questions and littered with the gravitational fingerprints of objects we have not yet identified. Planet 9 is the most famous of those potential objects, but it is not the only one. The darkness beyond Neptune is vast enough to hide not just one planet, but an entire population of worlds that we have barely begun to imagine. And so the search continues, not with certainty, but with the disciplined hope that defines science at its best. Telescopes will scan, algorithms will sift, candidates will be proposed, tested, and either confirmed or discarded. The process is slow, the stakes are high, the outcome is genuinely unknown. Somewhere beyond the orbit of Neptune, in a region of space where the sun is just another star and the temperature hovers a few tens of degrees above absolute zero, there may be a world waiting to be found. A world that has orbited in silence for billions of years, unseen by any eye, unrecorded by any instrument, unknown to any civilization that has ever existed. If it is there, it has been there since the beginning, and it will remain there, circling patiently in the cold, whether or not we ever manage to see it. The universe does not require our confirmation to exist, but our understanding of it depends entirely on what we can find. the courage and the patience to look for.